Hello friends, in the last lecture we have discussed few examples which are based on case number 4. Now in today's lecture we will discuss case number 5 to find value of particular integer. So when capital X is given as x into v, small x into v, where this capital V is any function of small x, then in that case our target 1 upon f of d operate capital X. Capital X is what? X into v is equal to what? X into 1 upon f of d operate v on it plus d by uh, d capital D of f of d operate v on it. So our target is to prove here this one result. So in general we know what is pi. In general pi is 1 upon f of d operate capital X on it, and capital X is given x into v, and this is our case number, what we call it as a 5. So capital X is given as x into v, where v is any function of small x. Then how to find the pi? So here we will take here u be a function of small x. We will take similar to case number 4. We take eve as a function of small x, and we know if eve and v are functions of small x, then what is the Leibniz theorem? We have studied here that theorem under the topic successive differentiation. So what is that theorem? D raised to n of uv means nth derivative of uv is equal to d raised to n of u into v plus nc1 d raised to n minus 1 of u into dv plus nc2 d raised to n minus 2 of u into friends here wrongly written here cot, this must be dot like this one, here d square v plus on e into d raised to n of v. Means here actually we have studied here u n v. U n means nth derivative of u, and nth derivative of u we can write d raised to n into v plus nc1 n minus 1th derivative of u, means here d raised to n minus 1 of u into v1. V1 means dv, that is first derivative of v, plus nc2. Here un minus 2 is there. Un minus 2, its meaning is d to the power n minus 2 of u, means n minus 2 derivative of u into, this must be into uh, phi2. Phi2 means second derivative of here v, that is d square v plus on last term you will get u into vn. Its meaning is u as it is, vn means d raised to n of v. So using Leibniz theorem 1 means this theorem, we have d raised to n of x into u, d raised to n of x into u. Friends, here we have x into v, x into phi, but here we have taken x into u. X into u is equal to what it gives? This is d raised to n of u into, I can write it to be x or Evex. So while using Leibniz theorem, we need to select here the two functions, one as Ev and other as V. So you select the function phi in such a way that its nth differentiation or its derivative after successive differentiation becomes 0, and you select here phi as x and small u equal to capital U, and use here this theorem. So there you will get d raised to n of small u we have replaced by capital U into phi, phi means here x, plus nc1. There you will get d raised to n minus 1 of u into here dv. dv means derivative of this x with respect to x, and that is nothing but 1. So this can be written as, this x is taken here, d raised to n u plus here nc1 is n. nc1 is n into d raised to n minus 1 of u, or d raised to n of x into u. This x into u is equal to what it gives? X into d raised to n of u plus here uh, n into d raised to n minus 1. N into d raised to n minus 1 is nothing but what? D by d derivative of d raised to n with respect to capital D. So we have replaced here this n d raised to n minus 1 as derivative of capital D raised to n with respect to capital D, and this u remains as it is here. Since f of d is a polynomial in D, hence from this equation 2, so whenever d raised to n is here, you have to replace it by f of d. So if you replace this d raised to n by f of d, there you will get f of d x into u is equal to x d raised to n is what? F of d e as it is here. Then here d by d by dd of d raised to n u replaced by f of d, this u remains as it is. And then put this f of d into u is equal to capital V. So if you replace this f of d into u is equal to capital V, what happens? Operating 1 upon f of d on both the sides of this. 1 upon f of d on both the sides of this. There you will get 1 upon f of d, f of du is equal to 1 upon f of d, phi as it is. And from this, we get value of u as 1 upon f of d into v. Value of u from this, you will get 1 upon f of d into v. So friends, what we have to do, you replace this f of d into u as v, and you replace what? U, this u, and here this u replace by 1 upon f of d into v. So you will get from this 3, the next step you will get it to be like this one. Here, since e is a function of small x, so v is also function of small x. So from 3, f of d here remains as it is, this f of d. Then f of d into u, f of d into u, this quantity, f of d, this remains as it is. This u replaced by what? 1 upon f of d into v. So that x remains as it is. U we have replaced it by 1 upon f of d into v. Then further is equal to, what is the right hand side? Right hand side is here x into f of d into u. X remains as it is. F of d into u is nothing but what we call it as v. So its value is substituted here, x into v, plus d by d of f of d as it is. D by d of f of d as it is. This d by d of f of d by dd of f of d remains as it is, and this u replaced by 1 upon f of d into v. So friends, in my sense, there is a no problem to you up to here this equation number 3. How here this proof follows. After this equation number 3, you put here this quantity is equal to v, and then operate 1 upon f of d on this function. So if you have operated 1 upon f of d on this function, there you will get 1 upon f of d of this LHS is equal to 1 upon f of d of this RHS. And from this function you determine u. So u equal to, it gives 1 upon f of d into v, and that is written here. So after here this step, what you have to do, you replace this what we call it as a f of d into u as a v, and whenever u is there, so u is present there here and here afterwards. So you replace this u by 1 upon f of dv, and here this u by 1 upon f of d into v, and you rewrite this equation 3. So you will get that equation 3 to be like this one. And then what you have to do, you operate here 1 upon f of d on both the sides of here this equation 4. So this f of d upon f of d gets cancelled. So LHS will get x 1 upon f of d into v is equal to, operate 1 upon f of d on this first term. So there you will get 1 upon f of d x into v as it is. And then here you remember friends, d by d capital D of f of d means what? That f dash of d. So we can write here this bracket by f dash of d, and that is written here. And if you replace here, if you have operated 1 upon f of d, then this 1 upon f of d and this 1 upon f of d, it gives f of d square. This v remains what? As it is. And further we can write here result for here this one statement, 1 upon f of d x into v is equal to, you see this term on LHS. So there you will get x 1 upon f of d v minus you will get here this term there. F dash d upon f of d its square, operate p on it. And further here, this LHS remains as it is, this first term remains as it is, and here this quantity, this v also as it is. This quantity is nothing but what? The derivative of 1 upon f of d with respect to capital D. So if we have taken derivative of 1 upon f of d with respect to capital D, there you will get denominator into derivative of numerator 0 minus numerator into derivative of this denominator, there you will get f dash d that is present here divided by square of this. Use here u by v rule for getting d by dd of here this function. So easily you will get the proof of here that one result, and you have to remember here this result because while if here capital X is given as x into v, then in that case we will use here this result for finding the value of particular integral. So in my sense, friends, if you understand here this proof of here this result, now actually what you have to do, friends, here if this rule is not applicable, if here this function f of d is given of the type d square plus a square, and v is given to be a sine x or cos x, there you will get denominator to be 0, and that's why what we have to do, we have to use here this alternative method, that is working rule for finding value of pi. So when capital X is x raised to m into sin x, or capital X is x raised to m into cos x, you have to use here this method for finding the value of particular integral. So in general here pi we can write 1 upon f of d x raised to m into, suppose sin x is given, x raised to m into sin x. Then this sin x we can write it as the imaginary part of cos ax plus I sin ax. This 1 upon f of d x raised to m, this remains as it is here. And this sin ax is nothing but what? The imaginary part of this complex number, cos ax plus I sin ax. And then further, this we can write it as e raised to iax. So IP of this remains as it is, 1 upon f of the x raised to m remains as it is, and this cos ax plus I sin ax, we can write it as e raised to iax. And friends, this becomes our case number 4 to find the value of particular integral. You forget about these words IP of, you carry throughout in the solution. So what you have to do after here this step, you take this e raised to ax outside, and whenever d in this f of d, you have to replace d by d plus ia, operate x raised to m on it, and further use case number 3 for finding the value of particular integral. Further here, if capital X is given as x raised to m into cos x, then in that case, this IP you replace by RP. RP means real part. So in that case, you proceed to find PI to be like this one. 1 upon f of the operate x raised to m into sin ax. Sorry, this must be friends cos ax. This must be cos ax is equal to real part of 1 upon f of the x raised to m. This remains as it is. And this cos ax we can write it as real part of cos ax plus I sin ax. Means real part of this complex number. And then further, uh, you substitute your value of cos x plus I sin x as e raised to ix. There you will get value of pi to be real part of 1 upon f of d. This part remains as it is, operate x raised to m, and this cos x plus I sin x, you replace it by e raised to ix. And now friends, here this becomes what we call it as a case number 4 to find the value of particular integral. Means you carry this RP of in each and every step in the solution, and here this becomes case number 4, means you take this e raised to x outside. Whenever you are d in f of d, you have to replace it by d plus ia, operate x raised to m on it. And then further, friends, what you have to do further, uh, use case number 3 for finding the value of what we call it as a particular integral. So in my sense, if you understand here this part, and we will use here this method for finding the value of what we call it as a pi, when capital X is given as x into v, or here x is to m into v. In both cases, we will use here this method itself for finding the value of particular integral. If sine function is there, use result here 1 means here this result, and if cos function is there, use result here this one for getting the required value of particular integral. So here very simple example is given. See only one example. Rest problems we will discuss in the next lecture. So solve here d square plus 9 into y equal to, suppose given, x into sine x. So this is in the form x into v, x into v. So its auxiliary equation, you will get f of d equal to 0, that is d square plus 9 equal to 0. It gives d square equal to minus 9, and taking square root on both the sides, there you will get d equal to plus minus 3i. So you compare here, you write this as 0 plus or minus 3i, and you compare it with alpha plus or minus beta I. There you will get alpha equal to 0, beta equal to 3. So CF you will get e raised to alpha x, that is e raised to 0x, into c1 cos beta x, beta is 3, means there you will get c1 cos 3x, plus c2 sin beta x, beta is 3, so there you will get c2 sin 3x. And then by both the methods, I will show to you how to find the value of what we call it as a particular integral. So what is here method 1? Method 1 means we will use here this method. So pi equal to 1 upon d square plus 9, operate x into sine x on it. So sine function is there. If sine function is there, you take imaginary part. You take imaginary part of e raised to ix. That is nothing but sine ax. So we will take here imaginary part of 1 upon f of d x raised to m, means here this part 1 upon d square plus 9 x, operate x on it, this remains as it is, and this sin x, we have replaced it as ip of e raised to ix, ip of e to the power ix. And further here, this ip of these words I have carry here in the next step. This is our case number 4. So what you have to do, you first operate e raised to ix here. So if we have taken e raised to ix outside, what we have to do, whenever d here in the denominator, you have to replace it by d plus a. So a is nothing but coefficient of x, that is I. So replace here d by d plus I, bracket square plus 9, operate what, that x on it. And if you simplify this, this ip of e raised to ix remains as it is in the next step. If you simplify this denominator, there you will get d square plus 2id plus I square, but I square is minus 1 plus 9, there you will get plus 8. So that is our next step. So IP of e raised to ix as it is 1 upon d square plus 2id plus I square means minus 1 plus 9, you will get plus 8, operate x on it. And this is our case number 3, friends. This is our case number 3. So what you have to do, you have to see the lowest degree term in the denominator, and that is nothing but 8. So divide here numerator and denominator by 8, so that we can obtain here denominator is in the form 1 plus function of d. So if we divide numerator and denominator by 8, numerator takes the form 1 by 8. This IP of e raised to ix as it is here, 1 by 8. And see the denominator, 8 divided by 8, you will get 1. Plus, you will get these two terms divided by 8, and that is written here, operate x on it as it is. Then this 1 by 8 from this numerator, I will take outside here, because it is constant, into, we can write ip of e raised to ix as it is, and write here this function in numerator as raised to minus 1. 1 plus function of d raised to minus 1, operate x on it. Further here 1 by 8 as it is, ip of e raised to ix as it is, and expand this by using the series 1 plus x bracket raised to minus 1. So there you will get 1 minus x plus x square minus x cube plus so on, operate x on it. So x you replace by this quantity d square plus 2id divided by 8. Further here 1 by 8 ip of e raised to ix remains as it is, and now you operate here this function x on each and every term inside this bracket. So 1 into x, there you will get x. This 8 is taken to be outside, so 1 by 8 you will get here. Here remains d square of x. D square of x means second derivative of x with respect to x, and that is 0, because first derivative of x with respect to x is 1. So second derivative of x with respect to x, you will get it to be 1, sorry 0. So d square of x, you will get it to be 0, plus 2i as it is, and d of x, you will get it to be what? that you will get it to be 1. So 2I into 1 you will get 2I here. If you observe here this term, it involves minimum power of d. If you simplify this numerator by using the result a plus b bracket square, this 1 upon 8 square, that is 64, is taken outside. Then what is left here? D square plus 2id bracket square. It involves here minimum power of d to be 2. And we know second derivative onwards, all derivatives of this function are 0. So you don't consider the terms from this term onwards, because this term involves minimum power of d to be 3, 2. Next term involves minimum power of d to be 3, and so on. And that's why, friends, you don't consider rest of the terms. Only you simplify this. Now in the next step, this IP of e raised to ix, I have substituted here value of e raised to ix as here cos x plus I sin x into here this bracket as it is x minus 2 upon 8, you will get it to be 4, and this I as it is. And now what you have to do, you take the product of here these two brackets, and we want imaginary part of here the product of here these two brackets. Means you have to consider here the terms containing I in this product, but don't write I, or before it I have taken this 4 to be outside. So 4 into 8 you will get here 32. Here IP of remains as it is. Here cos x plus I sin x as it is. Here you will get 4x minus I. And then you take the multiplication, and only you consider the terms in this product of these two brackets containing I. Though, these terms gives what we call it as the imaginary part of the product of these two brackets. So cos x into 4x, it does not contain I, so don't consider. Here cos x into minus I, it contains I, so don't write I, only we have to write that function. So that function you will get minus cos x, that is written here. Then I sin x into 4x, it contains I, so you consider that term 4x into sin x, that is considered here. Then I sin x into minus I into I, you will get I square, its value to be minus 1. So you will get that term as a real term. So it gives here this as what we call it as a required value of the particular integral. And once you know pi, the solution is given as y equal to cf plus pi. So friends, in my sense, you understand here this method. Suppose your friends, in this example, instead of your sine function, if it is given cosine function, then here you replace this sine by cosine function. Rest part remains same as it is. Only you take instead of I there r. R means real part, and in that case, up to here this step you will get the same solution. There will be no change up to the second last step. Only in this product you have to consider the real terms. Real means the terms not containing r. It gives the required value of particular integral, that is 4x into cos x, plus it gives it to be sin x. 4x into cos x plus sin x, these two terms not containing I in the product of these two brackets, and that part you will get it as real part if instead of sine, cosine function is there in capital X. So in my sense, if you understand here the proof of that theorem, as well as here the example which is based on that theorem, we have solved here this example by using that second part, means by using here what, by using here this part we have solved the example. Now in next lecture I will show to you by using here this result also, it gives here the same value of particular integral. So today maybe it is possible for me to explain it, but the lecture becomes very lengthy, and that's why we will discuss here how to find here pi, same pi, by using here this formula. But we will discuss here that part in the next lecture, and that we call it as a method 2 that I have shown here. You have to remember, but we will discuss that part in the next lecture. So I have a good day, friends. We'll stop here.